Hi everyone, welcome back to the lecture 3 of our Möbius inversion mini-series. In lecture 2, we define the function mu. Now, here we know that its value depends on the square-free structure and the parity of distinct prime factors. Now today, we're going to go one level deeper. Now we're going to understand mu n for any integer just by understanding the values on the prime powers. The key idea is the property of multiplicativity. That is, when two numbers are coprime, the mu of mn equal the multiplication of mu m and mu n. Okay, so this property turns mu function from a quirky sine function into a powerful building block that interacts cleanly with divisor sum and Dirichlet convolution. All right, so this would lay foundation for further effects of the inversion formula. Now, how to watch this lecture? We're gonna again to listen to the teacher-student dialogue. We're gonna build intuition first, and then walk through some examples. Now, in the next lecture, we're going to talk about convolution and inversion formula. Let's go into the lecture.
On this slide, you see a question about the Möbius function. When two numbers have no common prime factors, can the value of mu on their product be written as the product of mu on each number separately?
So, if I already know mu of m and mu of n for a coprime pair, the big idea is that I might be able to get mu of m times n just by multiplying those values?
Exactly. And that property is called multiplicativity. Our goal today is to understand what it means in general and why the Möbius function has it. Here is the general definition. A function on the positive integers is multiplicative if, whenever two numbers are coprime, its value on the product equals the product of its values. The equation at the top captures this idea. For coprime m and n, the function value at m times n breaks cleanly into the value at m times the value at n.
So multiplicative functions respect multiplication, but only when the two inputs share no prime factors at all.
Before proving anything, we recall how the Möbius function is defined. It sends 1 to 1, sends a product of k distinct primes to -1 raised to the k, and sends any number that has a repeated prime factor to 0. So mu has two jobs at once. It detects the presence of a squared prime factor, and for square-free numbers, it records whether the number of prime factors is even or odd through the sign.
Right, so numbers like 6, which is 2 times 3, get mu of 1, while something like 4, which is 2 squared, gets mu of 0 because of the repeated prime.
To see why mu is multiplicative, we assume m and n are coprime and split into two cases. If either m or n already has a squared prime factor, then the value of mu on that number is 0, and the product m times n also has a squared prime, so its mu value is 0 as well. In the other case, both m and n are square-free and have disjoint sets of primes. Then we can write mu of m and mu of n as -1 to the power omega of m and omega of n, where omega counts distinct prime factors, and mu of the product uses omega of mn.
Because the primes are disjoint, omega of mn is just omega of m plus omega of n, so the sign for mu of mn is the product of the two signs. That is exactly the multiplicativity rule.
Now we test the theory on concrete numbers. The equations show that mu of 2 and mu of 3 are both -1, so for 6, which is 2 times 3 and is square-free, the multiplicative rule gives mu of 6 equal to 1. For 30, we factor as 2 times 3 times 5, 3 distinct primes, so we multiply 3 copies of -1 and get -1. The small table reinforces how the prime factorizations line up with the mu values.
So as long as I can break the number into coprime pieces, like single primes, I can just multiply the known mu values to get the answer for the whole number.
This slide shows the key simplification. For a prime p, mu of p is -1, and mu of any higher power of p is 0. Once you know these prime power values and that mu is multiplicative, You can determine mu of any integer just by factoring it. The formula at the bottom introduces Dirichlet convolution, a way to combine two functions using a sum over all divisors of n. Multiplicative functions behave especially nicely under this operation and often let us break such sums into independent prime power pieces.
So mu is not just a random sign function. Its simple behavior on prime powers plus multiplicativity makes it a powerful tool when we build divisor sums like this convolution.
For practice, look at 12. We can factor it as 3 times 4, and these two factors are coprime. From the prompt, mu of 3 is -1 and mu of 4 is 0 because 4 has a squared prime. So multiplicativity gives mu of 12 as their product, which is 0.
That makes sense. 12 has a factor 4 that already forces mu to vanish, and I saw that just by using the prime power rule for 2 squared and then the multiplicative rule for 3 times 4.
Exactly. Reflect on what you just used. Knowing mu for prime powers, plus the fact that mu is multiplicative on coprime factors, was enough to handle this composite number quickly.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.